Hi, I hope you're doing awesome. So the question we are seeing today is curious case of Benjamin bulbs, right? So what this question states is that we are given n as an input, which actually determines that how many number of bulbs we have. Suppose it's 20, for instance. So we have 20 bulbs and they are being toggled. So what being toggled actually means is we change the state of the bulb, right? If it's initially at off position, we switch it on, and if it's at on position, after one toggle, it will become off again, right? So this is what toggling means. Now we are given 20 bulbs that are, let's write them down, right? One, two, three. Let me complete it. So these are all the bulbs. Now they are being toggled. That is, when I toggle for number one, suppose n equals to one, I toggle n times. So all the multiples of one are toggled. That is, every bulb will be toggled in the first case, right? For n equal to 2, right? For the second toggle, only multiples of 2 will be toggled. For n equal to 3, only multiples of 3 will be toggled, right? And we toggle them 20 times. So in the first toggle, every bulb will be toggled because every bulb or every number is multiple of 1. So let's put a tick for each bulb toggled. That is here, right? So initially every bulb was at off position. So in first toggle, every bulb will be switched on, right? It's a lot of hard work as of this moment, but you will understand that why I have taken such a big number of n, right? Now, what the second toggle for the second time, only multiples of 2, that is 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. These are the bulbs toggled. For n equals to 3, or the third iteration, only multiples of 3, that is 3, 6, 9, 12, 15, and 18 will be toggled. For n equal to 4, 4, 8, 12, 16, and 20 will be toggled. For n equal to 5, 5, 10, 15, and 20 are toggled. For n equal to 6, right here. For n equal to 6, 6, 12, 18 are toggled. For n equal to 7, 7 and 14 are toggled. For n equal to 8, 8 and 16 are toggled. For n equal to 9, 9 and 18 are toggled. For n equal to 10, 10 and 20 are toggled. Now, for n equal to 11, actually 11 is the only multiple in this range. So only 11 will be toggled, right? Actually, yeah. And it should be. So this is one tick because for n equal to 1, and this is second tick, n equal to 11. For n equal to 12 now, only 12 will be toggled. For n equal to 13, 14, 15, 16, 17, 18, 19, and 20. Let's see that which bulbs are remaining on after all the toggles are completed, right? Let's see. So let's suppose one was initially off because, as I told you, that initially position of every bulb was switched off. So after one toggle, it will be switched on. So this is the bulb that remains on, right? N equal to 2, it was the second bulb. It was turned on and then off. So we won't be highlighting it because it remained off after all the toggles are completed, right? N equal to 3 also, it was turned on and it was turned off. On, off, and on. So we highlight this 4. For n equal to 5, it was switched on and it was switched off. N equal to 6, on, off, right? So as you must have guessed by now that the bulbs which have toggled for odd number of times, right, will only be remaining on at last. So let's see which are the bulbs. This is 9. Let's see, 1 2 3 4, 1 2 1 2 3 4 5 6, 1 2 1 2 3 4, 1 2 3 4, 1 2 3 4 5. So 16 has remained on. Now 1 2 3 4 5 6, 1 2 1 2 3 4 5 6. Yeah, so these are the only bulbs that have remained on, right? Let me zoom out a bit. Now let's see, there is a common thing about all the numbers that have switched on, that is first, fourth, ninth, and 16th, that they are perfect squares. So the question is actually solved at this moment, that any bulb which is at the perfect square position will be remaining on after all the toggles are completed. But let's see why is this actually making sense, right? Now, to understand that, let's see. We'll see that how many factors of any number are existing. Suppose if we have any number such as 12, if it has even number of factors, then it will eventually be turned off, right? And it has, if it has odd number of factors, then it will be left on. So this is the case. Now let's take any number which comes to mind. Suppose 24, right? So let's write all the factors of 24. That is 1 into 24, 2 into 12, 3 into what is 8, 4 into 6. Then after that it gets mirror imaged, right? 6 into 4, 3 into 8, 12 into 2, and 24 into 1. But let's see what happens in the case of perfect squares, that is 36. Then it gets 1 into 36, 2 into 18, 3 into 12, then 4 into, I don't know, 9. Yeah. And after that, this is the moment which is actually important. It is 6 into 6. But mirror image of 6 into 6 won't be happening because it will result into the same factor, right? Now, it will be 9 into 4, 12 into 3, 18 into 2, 36 into 1. So, as we can say, the factor of any normal number will be 2 of n, right? Because these are the numbers and these are the mirror images, which is equivalent in numbers. But for the perfect squares, we have an extra factor here, that is root of n, which makes the number of factors to be 2n plus 1. And this is the why it's actually remaining switched on in the end. Let's try to code it now. The code is very simple if you have understood this. So we make an object of the scanner class. System.in. Right. We take an input scn dot extend. Now we'll run a loop for int I is equals to 1 and I star I is less than equal to n and I plus plus, right? Just a second. Yeah, and we print system dot out dot println, not I but I star I, right? Yeah, so hopefully this should work. And we have a compilation error that it has reached end of line. Let's see where. Yes, of course. Right, so it's getting accepted. Let's try to submit it. So it's getting submitted. So I hope you liked the explanation. If you did, kindly press that like button and subscribe to the channel. Thank you very much.